So, hello everyone. My name is Lucas. I will be talking today about replacing smart cards with the Linux kernel. This is a view from the user space. I'm not a kernel developer, so let's get started. So, the agenda for today is an overview of smart cards, so we are in the same page of what they are, a few problems that we can encounter when using them, and the current state on Linux, how it's done in other platforms, a brief introduction to the Linux kernel key retention service, which is a feature of the Linux kernel that can hold cryptographic material. Uh, Brief talk on trusted keys, and then a definition of a cryptographic boundary, which will be very important, and future work to make this possible. So the idea here is not to show a finished product, but to start a discussion on this if this is something we want to do in the future. So what are smart cards? They are essentially like credit cards. They have a SIM interface, which is essentially a USB interface, and they are used to store things and control access to a resource. So if you have a debit card, it will control access to your money that's in your bank. That's the idea. They can have a crypto processor that for doing cryptographic operations. This can vary a lot. It can support hashing. It can support only symmetric key operations, asymmetric key operations, or whatever. Uh, they are largely used by government. I think in Europe as well. It's very common to find this in EIDs. Uh, and the most common interface that you will get when you're using one of these is PKCS11 on Linux, uh, which usually is uh, a binary blob that is vendor provided, proprietary, and this is also known as a token. So current state on Linux, we have OpenSC, Open Smart Card, uh, which is I think the most used application for interacting with smart cards and tokens. They did an incredible job on fixing a lot of issues you encounter with this, especially issues with the S11 interface. There's NSS, libNSS. This is used by Firefox. You can use Firefox to load certificates, sign things, access government resources. There's OpenSSH as well, which can load and use tokens, GPG, and a few more. There's interfaces for OpenSSL and so on. Okay, so what is PKSS11? It's basically a standard developed by Oasis now that defines the CryptoKey API, which is the API you use to interact with the token. It uses a object-based approach to do this, and is designed basically to be completely independent. So you can do everything on any device. It is a very complete API. It can do everything a certificate authority needs to do, issue CLRs, revocation lists, everything, and it is implemented as a shared object most of the time, and this is a big problem. The API as well is API, no, the spec as well is not really a spec. I would say it is a suggestion because if you ever used one of these in the wild, you find that most vendors will make their own conclusions of what they're trying to do, and most of the time it will work. Most of the times you will spend a few hours trying to fix issues and trying to get the token to work, and we'll have a look at a few of those problems now. So PSS11 is tricky to use. On the first function that you use before initializing before getting the list of functions supported by the PKCS11 version, which is cinitialize, it takes a void pointer, which is actually a CKC initialize args struct. And inside this struct, there is a field called CK flags, and it holds a few important values. You can basically fail here because the token does not support, it's not mentioned actually in the spec that if the token will support or no parallel or concurrent access. And I've seen numerous cases of this where a few vendors took a few decisions in supporting this. So if you pass no, it will work. Maybe sometimes with another vendor it will not work, and you can just it's very hard to use. So let's proceed. It is also, being a shared library, it makes use of the runtime dynamic linker. And here we can also encounter a few issues, primarily with symbol collision, which means that if you have a binary linked against a version, let's say of OpenSSL, and you load a token that was linked against a previous version of OpenSSL, let's say OpenSSL 1, you can get symbol collisions and it will simply not work. And there's a big issue with non-static object lifetimes, which basically means that the runtime dynamic linker has no knowledge of what is happening. It just maps the pages, sets the addresses correctly, and so the code can execute correctly, but it doesn't know if the loaded code created a thread, it did a mapping, or if it opened a file. So we're looking at an example of this now. This is a piece of code that is basically an exploit for that. We have an mmap that creates a mapping. So the runtime dynamic linker, in this case with the glibc implementation of DLOpen, it doesn't know this mmap, and you can use this to basically run arbitrary code. And I'll give a demonstration of this now. So you can see here, I just printed the maps of the process with proc self map, and we can see the mappings. Here's the few executable pages here and here. And if we proceed, you can see in the bottom here, creating a thread. It will print another mapping, and you can see that we have a page here that survived unloading the library with the alcrolos. And you can see here, hello from lib1. After loading lib2, which is just a simple program that prints hello from lib1 in a loop a few times. And you can see that our thread survived. This can be very disastrous if you have multiple tokens. And if you are forwarding a token to another machine that has another token plugged in, this can lead to basically anything happening. Luckily, most libraries are not vulnerable to this. OpenSSH is not, but most of the others, I think, are, but it's a very rare problem to encounter and a little bit obscure as well. So if there is an issue with supply chain attack for the token that was provided by the vendor, it could lead to issues. And this brings us to the next point. How it's done in other platforms. It is basically the same idea with shared objects, but with different APIs. Windows has the CSP, which is the cryptographic service provider, and the key storage provider. These are also implemented as shared libraries, and there's a new API, which is the CNG, also implemented as a shared library, and is better integrated in the system, including browsers can load certificates from these APIs. Only Firefox can do this. macOS has a keychain, which can load tokens via the Crypto Token Kit framework, which is very obscure and requires almost reverse engineering to implement. And I think BSD is the same as Linux. I don't have knowledge. If anyone has knowledge on that, please correct me. So I asked the question: can Linux do better? We can. We have something called the Linux kernel key retention service, which is a feature of the kernel, which allows keys to be stored in the kernel. This is a very old feature, but is very underused, in my opinion. In this model, everything is a key. It is analogous to a file system, but instead of a file, we have a key. There are several types of keys. There can be asymmetric keys, trusted keys, user keys, which are basically format independent and opaque in that sense. So OSC uses this to store your password. There's an option to do that. And they have a few permissions: view, read, write, search, link, and set attributes, which is the group ID and the user ID. It is controlled by a syscall interface. The main three syscalls are add key, which you use to add a key, which is composed by the first parameter being a type, the second one being the description, which is basically a name you can give it to it. The third one is the payload. Fourth one, the length of a payload, and the last one, the keyring. And this brings us to the keyrings. There are several types of keyrings, including process keyrings, thread keyrings, which are created and last only for the lifetime of that thread or that process. There are session keyrings, there are persistent keyrings, which last even if all processes of a group ID or user ID have perished, so it will continue to work. And this can be used to implement things like daemonless daemon, which via this second syscall request key can be used to provision keys from, let's say, an HSM that is somewhere, or even you can set up that you can share your key repository on your computer to another computer. So, and lastly, there's the keyctl syscall, which is basically format dependent for the operation. Here we have the sign operation, which takes a few parameters, the info, which controls like the encoding and the hash used, and in and out parameters. And how would this be used in something like the SSH agent or the GPG agent? Essentially, here you have a file system with an encrypted key in the file system. You would load this key by decrypting it and then sending it to the agent. The agent would cache it in OpenSSH. This is done in memory. The key is stored in memory. It is protected by a symmetric key, but the key is also stored in memory. So it is a deterrent, but not bulletproof. And with the kernel, this could be improved. The key could be loaded into memory, decrypted into memory, and then stored in the kernel. So the amount of time the key would stay in memory and be visible to an attacker is very low. And there's another option as well where you can load a key into the kernel via the add key syscall, and there in this case there is no cryptographic material that is visible outside of the kernel, and in this case the user space would interact with this key via an ID. So I have prepared a demo for this, but unfortunately it didn't work on Tumbleweed because apparently the kernel doesn't support all of this, and I am pretty tired because of jet lag, so we'll link the demo later once it's fixed. So sorry about that. And this brings us to our few last slides, which is the notion of a cryptographic boundary. So NIST defines the cryptographic boundary as a explicitly defined continuous perimeter that establishes the physical and or logical bounds of a cryptographic module and contains all the hardware, software, and or firmware components of a cryptographic module. So this basically means that, let's say in the case of a token, the cryptographic boundary will be a physical boundary. The keys are in the token. If they are not exportable, they will remain there forever. And in this case of a logical bound, there is this notion of the virtual memory isolation. And while this invariant holds, we can assume that the cryptographic boundary is sound because user space will not see the sensitive cryptographic material, and only the kernel will see it. So, and this brings us to the notion of trusted keys, which is a recent development of the kernel. They are symmetric keys bound by a trust source, and they establish this cryptographic boundary between the kernel space and the user space, and they would allow us to basically implement this notion of of the cryptographic boundary for the Linux kernel, and use it as you would use a smart card. This is also used in a few HSMs that have high storage. You have a few master keys, and you can share these in different instances. They will all be able to decrypt the key and use it inside the HSM, even though the key lives outside the HSM. Yeah. For options here, a few notable ones are that the kernel supports the key out, blob out. It supports binding the seal to a PCR lock, so you can maintain the integrity of the system. And it also supports migrating keys, which is very hard to do from user space if you're using the DSS stack from Intel or from IBM. And this is our last slide. I wanted to bring the discussion of what to do next. The kernel can support more types of keys. This infrastructure is already present. I think there is patches for GPG keys, but we could also add SSH keys. There's also possible future work in upstream with GPG, SSH, OpenSSL, maybe with a provider. There's also work that could be done to generating keys in the kernel so that they can be generated inside the cryptographic boundary. So there is not this period of time where the key is outside of the kernel and the sensitive cryptographic material is exposed. Also, asymmetric encrypted keys. There's also a lack of standardization for URIs for the request key, which is also could be improved, and developments for post-quantum cryptography. So I expect a lot of questions, and thank you. Someone?
I guess I'll go first. There is no currently support for generating keys inside the kernel.
No, I don't think there is. Last time I've tried it, it wasn't there.
Oh, thanks.
Yeah, if I understand correctly, one of the kind of key that the kernel is storing is backed by the TPN. I think that is the one that PCR that the one that can migrate keys between with independence of the if you're using the stack for Intel or IBM. So I think that was presented on Fosten maybe this year. What is the current status of that? Can we use this type of kernels K-ring, or is it still not merged? So it's ready to be used, or we need to wait?
Yes, it is ready to be used. The kernel support the trusted keys and also asymmetric keys, but the only asymmetric, no, the encrypted keys, which would be the key that is sealed by this trusted key. But the only currently supported types of keys are for basically using file systems. So you cannot load a asymmetric key that was ciphered by the trusted key.